So, real quick, before we actually get into today's video, a commenter pointed out that I made a little bit of a mistake in last video. So, I was talking about when we have a short exact sequence. Oh, sorry, it should be E and G. And I was talking about how we define a G action on A. And what I had said in the video initially was that I was going to take a Y in G, and I was going to choose X in E, such that pi of X mapped to Y. And so I said in the video, I had said something about conjugating this by Y. But of course, this doesn't make sense because I of A is something that lives in E, and Y is something that lives in G. So this really should have been conjugation by X. So tiny little oopsie there. I think most of the argument still works out just fine. And or maybe, I had said that this was, I called this I of U. And then I said that this was going to be equal to I of V for some V. And then again, in the proof where, in the part where I was talking about the well-definedness, I then took a Z that was in E. And so again, I made a little oopsie. I had talked about the coset of X being equal to the coset of Y. But again, that's a little oopsie. That really should have been Z. Sorry. Yes, Z. Yeah. Okay, so that's it. That's all. Let's get on with the rest of the video. And welcome back. We're going to do some more cohomology. So, picking up where we left off last time. So, remember the setup for us was that we had a short exact sequence of groups. Let's see, I wrote it slightly differently. But we wanted to find every way. I mean, in general, we'd like to answer every way of putting two groups together. But for now, we are contenting ourselves with the case when the normal subgroup is abelian. And we determined last time that when this is the case, when we have such a short exact sequence, that this is equivalent to giving a G action on A. So this, or equivalently, this gives a ZG action, turns A into a ZG module. And the other thing was that we found we could model this extension. So not only were we able up to isomorphism to describe that group, but actually the entire short exact sequence in terms of equivalences of short exact sequences could be made. I'm going to draw over myself here. I hope it's not too jarring. Could be modeled in the following way, where we had some particular function that took in pairs of elements of G, returned elements of A, and EF, the underlying set of EF was A cross G, where we have a group law that was described in the following way. So it'd be A plus G acting on B plus F of GH, and then G times H here, right? So, okay, this tells us we can describe all such extensions by these functions. But now we ask, well, does every possible choice of function here give rise to such a group, to such an extension? And if that is also, whether or not that's the case, also we want to ask, if we pick two different functions, do we necessarily get distinct extensions or distinct groups. Like, in what sense is this a bijection? And if it's not, how can we correct this to get a bijection? So that's what we're going to talk about today, is cutting down the search space and seeing what, if any, other conditions have to exist on this F. So first, note that if I have any function like this, and I want to define a group law on this set of pairs, then notice that AG times minus G inverse acting on A minus G inverse acting on F G inverse times G inverse. If I plug this into my group law, then what am I going to get? So this will be A minus, so I mean, we have G acting on this thing, so it's G acting on G inverse dot A, but this is a group action by what we figured out last time, and in fact it's not only is it a group action, but it respects the abelian group structure here. So this just turns out to be minus A, and again we're hitting this up with a minus F G inverse. And then now we've acted on everything in the second component. We need to add the function, which is f at G inverse. And then in the second component, it's G times G inverse. So what does that mean? Well, if we look, all of these terms in the first component cancel out, and so do the terms in the second. So in fact, we have at least a right inverse. So, because what are we doing, right? We fix this function. We're trying to see, can we prove that this thing in the middle, just with defining this group law, can we prove that this is always a group, right? So what should we check? We need there to be inverses. What about, but we need inverses to be two-sided, right? So let's try and multiply this on the other side. So G inverse dot F G inverse here times AG. So multiplying things on the other side, we have minus G inverse dot acting on A minus G inverse acting on F G inverse plus, so now we need G inverse to be acting on A, and then we need to add F G inverse G, and then in the second component it'll be G inverse G. And so we find, well, this term will cancel out with this term, but we find now one of the restrictions that we're going to need to impose on this function, F G inverse G E, right? If we want this to be a two-sided identity, this term, or sorry, a two-sided inverse, this term here had better agree with this term here, right? But that is only going to be possible if this thing in the second term is equal to the identity. So this means that not any function will do, but we've cut it down at least to this restriction. So that's good, right? This cuts down the search space a little bit. Necessarily, the functions need to satisfy this. And now we know, also going through this proof, if we do choose a function that satisfies this, we know that at least we can have inverses. Okay, great. We definitely have identity. I'll leave that for you to check yourself. Identity under this group law will just be 0, 0. Remember that this section is normalized. That's a key step here. So that part's pretty easy. Let me look at my paper here. So what's the one other thing that's missing in order for us to define a group? Well, we need associativity. So let's try and unpack that. So what am I going to do here? So first I will do AG times BH, and then I'll do that multiplied by CK. So if I multiply this out, what are we going to get? So this will be A plus GB. I'm not even going to write the dot here because there's a lot of writing. Hopefully using the earlier and later parts of the alphabet will help you to distinguish. A plus GB plus FGH time, and then comma in the second component GH, and now this will be times CK. So this will be A plus GB plus FGH plus GHC plus FGHK, comma GHK. Okay, and so if there's any hope of this being associative, this had better be equal to AG times BH CK. And now we simply carry out this multiplication. So we get AG times B plus H acting on C plus FHK, comma HK, equal to A, bear with me here, gang, A plus GB plus GHC plus GFHK, plus FGHK, GHK. Okay, so now we are trying to compare this term here. If there's any hope for this being associative, we need to compare these two terms. So the A's match. G dot B matches. GHC matches. And what we find is we're left with the condition that we need FGH plus FGHK to be equal to G acting on FHK plus FGHK. So we have yet another restriction imposed on our function. If there's any hope for this function to actually define a group, we need this to hold for all GHK. And actually, it turns out that this is not an additional constraint to our previous constraint. So recall that we also needed this condition to hold. So let me do a little Control C and transplant this down here. Ooh, that's not what I meant to do. Okay. What did we need? We needed, okay, let me just minus G. So, if we take this to be our G, we take this to be our H, and we take this to be our K. So G inverse, G, G inverse, right? And I plug that in everywhere here. So this should be F of G inverse G plus F of G inverse G, G inverse equal to G inverse F of G, G inverse plus F of G inverse G, G inverse. Well, this is the identity, and this is the identity. And because this is a normalized, we're always choosing F to be normalized, we find that indeed we have the, this gives us the identity that we were looking for up here. So actually, the restriction imposed on us by demanding associativity implies the condition that we needed to have two-sided inverses. So that's great, because we know that actually now this is the defining condition. This is exactly, so if we have any function from that takes in pairs of elements of G to A that satisfies this condition, we know we can define a group, and we know that every single possible way of extending extending G by the group A will be of this form. So this is fantastic, right? Because we can just go through and compute functions. Of course, for big groups, this becomes a bit of let's say an issue, or how should I say it? Yeah, I mean, it becomes difficult, but at least now, instead of abstractly looking for these groups, right, it's a very straightforward problem. It's just, we have these equations, you could put it in a computer algebra system and iterate through them. But we also have this question of, well, does this overcount things? And indeed, so somewhere along the line, if you recall in the last video, I did highlight that there's a certain choice, there's a certain dependence here that I made sure to highlight. And that was the fact that, remember that this whole story, this choice of F, right, that we had started with when we were going the other way. So we just showed how to take any F satisfying that condition and go build such a group. But we want to know, right, when is that process injective, let's say, or to what extent does it fail to be injective? And remember, when we were building this whole thing, we started, our choice of function F actually depended, if you go back, watch the other video, it actually depended on the choice of set theoretic section that we began with. So we want to account for that. So suppose T is some other normalized section. Suppose we had chosen a different normalized section. Well, then pi of TG SG inverse, because pi is a homomorphism, we can split this up into pi of TG, pi of SG inverse. And so, well, both of these are set theoretic sections. And so we know that this has to return G and this has to return G as well. But now we've got that inverse. And so this has to be the identity of G. So again, because this element lives in the kernel of pi, and this is a short exact sequence, we know that this element has to lie in the image of A. And so that means that there has to exist some element of A where if we apply our map I, we will get this element here. And so I'm now going to give a name to that element. So think back just how like we were defining the function f, for example. I'm going to name that element C of G because it depends on G, right? So now again, I get another kind of function, right? So this is a function C that just goes from one copy of G into A, right? And how's this function defined? It is exactly going to be the function that returns the value of A such that when I apply I get out this term, which I know can always be done, and done so it can always be done by the exactness at the middle term, and it can be done uniquely by the injectivity of I, which is to say the exactness at the first term. So this really is a well-defined function. Okay. So the question is, how does changing this? Oh, and by the way, in this case, we have the following relation. So just multiplying things over, we know that the function t of g, or sorry, section. I mean, it is a function, but it's important that it's a section. So in other words, tg is equal to I of cg times sg. Right? And so now the question is, so what is the point of all this? Remember, we took our function f. That function f, its definition technically depended on this choice of section S. What we've done is we took an arbitrary other normalized set theoretic section T, and we found out that actually it has to be related to S in this way. And so we want to know, if we took the function that used T as its definition, how does that change in terms of this in relation to the original choice of section S? Okay, so in order to investigate that, bear with me for a second. So we're going to look at I of C of G. Sorry, didn't mean to put brackets there yet. I of C of G. Oh, there should be a bracket there. I of C of G times S of G times I C of H times S of H. So recall from the definition of the G action on A, which we talked about in the last video, the inclusion of CH, I mean, that is basically the result of G acting on CH. And remember, that action was defined in terms of the section SG. So this will be SG inverse I of G dot CH SG. So these terms would have been on the other side here when we were defining what the G action is. So that's a formula from the previous video, right? So if we take this term here, we can rewrite it in the following way. So bear with me here for a second. This is going to be I of C of G times I of G dot CH S G S H, right? So that is this term. So maybe I'll explain that. So this term goes here. This term I can put in an SG inverse SG here, right? And now I'm rewriting this in terms of the action. And then I have left over the SG times SH here, right? So that's exactly what's happening. Now, okay, rewriting this further, what do I have? Well, I is a homomorphism. So I know that this is I of CG plus G dot CH. That's all one term. And remember how the function f was defined in terms of the section. It was defined in such a way that this should be f of GH times S of GH, right? That was just the definition of f from the previous video. And again, applying the fact that I is a homomorphism, I find that I is CG plus G acting on CH plus F of GH. And, oh boy, I have to make one other adjustment here. Yes. So we're also going to do our mathematician's favorite trick. So I'm going to again, we're going to add CGH. We're going to add 0, which is just CGH in both sides here. And give me a second. So I'm going to write here minus CGH, and then outside of this will be I of CGH times SGH. And so what's the point of that? So now if we go back and we look at the formula that defined the group product law from the previous video, what we should find is that the associated function, the what we would have called f, so remember the formula that we wanted to use in the previous video to line things up in the proper form. I'll refer you back to that. The function now that we would have called f, which goes from g pairs of elements of g to a, is now the function that takes gh and sends it to cg plus g dot ch plus fgh minus c of gh. So, in other words, we can view this as, so c is a function from GA. So we can actually, I'm going to write this as a function delta c as a function from copies, pairs of elements of G into A in the following form. So delta C at a pair GH is going to be CG minus CGH plus G dot CH. Okay. So what is the big takeaway? Well, writing it this way means that changing section, right? Changing section S to T changes the function f to f plus delta c. So what's the point of that? Well, if we think about what's going on here, right? We're starting with some fixed extension. Some short exact sequence. And if we change s and t, we shouldn't be changing the extension, right? Because we're just changing the choice of set theoretic function. So what that means is, if we take f plus delta c, that should give us the same extension. So in other words, what we want to be looking at is, in order to classify all extensions, so extensions of G by A, should be in bijection with the following thing. Well, it should be all of the f that satisfy this condition that we, so let me just skip ahead to I guess a main punchline here. It's going to be the following thing. So it should be in bijection with the following thing. We're going to look at functions from G to A. We have a map delta, which takes us, so remember, that was like our C. We apply C to C delta. We get out a function that goes from G squared to A. And I'm going to define another map D that goes from functions of 3 copies of G to A. So what is delta? I defined a delta above, right? So delta is going to take in a function C that acts on one variable and is going to return a function that eats pairs defined exactly in this manner. What is the D that I wrote? It's going to exactly be the function that, well, I'm gonna spit out this in a second. So how is the D going to be defined? So if we have an f that goes from G squared A, this D is going to take that and return a function on 3 variables. And it's exactly going to be f of gh plus f of ghk minus G acting on FHK minus F of G HK. And so what does that mean? Well, notice then that if F is in the kernel of D, so I'm claiming that this is in fact a homomorphism of groups. These have each of these function spaces, because the codomain is an abelian group, each of these function spaces itself has the structure of an abelian group. And notice that F being in the kernel means this expression is 0, which is exactly what it means for F to satisfy that condition that we figured out it has to satisfy. That's equivalent to allow us defining a group. But also notice that we found out that if we change F by any one of these functions, right, changing F by adding a delta C shouldn't change the extension. And so what we want to look at then is actually the kernel of this map D modulo the image of this map delta. So this is the kernel of D modulo the image of delta. And so what does that mean? So for those of you, I mean, at this point, a lot of you know where this series is going. This is exactly what one calls the second group cohomology of G acting on A. So that concludes our description of exactly how to determine all possible extensions of one group by another. I think what we might do in the next video is get back down to earth, do some basic examples in detail. So, you know, we've got things like maybe the quaternion group that we've dealt with, or, you know, these other short exact sequences that we figured out weren't products, and perhaps not even semi-direct products, right? So I think it's about time we come back down to earth with some concrete examples, and then we will probably ramp up the abstraction again to see, well, you know, this is the second cohomology group. So what are the first, what's the first cohomology group? And start taking a look at the broader theory that this all falls into. So until then, I would encourage you to try and do some of your own computation. So now you have the exact rule, right? There's this kernel modulo this image. You have everything you need to completely determine the second cohomology group really explicitly. Try it with some small groups, and you'll be able to see in the next video if you got the correct answer or not. And then you can actually work out the extensions yourself, right? Once you work out each of these functions, you could literally take that with the formulas we've defined. You could define these extension groups, and you can see which groups that you get out of it, which groups of small order. So I'd really encourage you to do that. But until then, I'm going to say QED.